So some of you may have seen James Pekel's talk yesterday talking about basically a microstructured on-chip battery. And so this, in some sense, will be some of the background for that, as well as some other directions that we've been pursuing. So really the way that in my group we like to think about these sort of problems is these are explicitly three-dimensional problems. If you think about energy storage requires a volume of material, and therefore it cannot be an exclusively two-dimensional system. And in fact, in a battery, if you want to, say, make the electrodes quite thick so that you could, say, store sufficient energy, if you try to do this as a two-dimensional problem, diffusion and transport will immediately shut your system down. You need long-range diffusion and transport, and so by definition, the system must be thin, but to store a lot of energy, it must be thick. And so how do you do that? And of course, the answer is that you structure the material. So this little guy isn't too excited about his 2D swimming pool, and I would say my group sort of thinks the same way about the problems that we approach. So of course, there's many different ways to make three-dimensional structures. A few years ago here, I talked about some of our work in optical systems. And for optical systems, you can certainly work in the world of high complexity, but rather high expense. If you're going to go into something such as energy storage, where realistically you're talking about tons of material requirements, not gram material quantities, really you're going to be limited over what I would say largely is in the self-assembly space. So the systems I'll talk about today are primarily based on colloidal systems, which can be done in large and scalable volumes. So what is a battery? Well, some of you may have made batteries before. In fact, all you have to do is go buy a solid fruit that has sufficient ions in the media and insert two different metals into that, and the work function of the metals will be different by some amount, and that will create a voltage. And so that's simple enough. And so this potato battery will operate until either the potatoes rot or that one of the metals dissolves and plates onto the other material. So that's simple enough. Now, of course, in a real battery, we want to have combinations of high power and energy density, scalability, reasonable cost. And so really that's been optimized today in these what are typical spiral wound batteries or variations of this. And this is what we find in virtually all portable electronics. And it consists of a multi-layer structure that is a cathode, a separator, and an anode. The separator's job is to allow the ions to move through, but not allow the anode and cathode to touch each other. If they touch each other, they short out. That generates a large amount of heat. The electrolyte is almost always an organic liquid. You get a lot of heat, and it catches fire. And so this has been known to occur. It occurred in laptops a while ago due to manufacturing problems. Little metal shavings were present in the battery that would punch a hole through the separator. Boeing, of course, has had issues with the 787 and battery problems. And primarily that's because some sort of heat evolution leads to a failure mode here. But if you want to have high power and high density, high energy, you want a lot of this and a little bit of everything else. So you can start to see the challenge here. You'd prefer to get rid of the separator completely, but then of course your battery would short out. So if we zoom in inside the battery, and this happens to be during the charging cycle here, the anode is typically a carbon-based material. Electrons can be inserted into that as well as lithium ions, and so the lithium is stored in very close to the metallic state. And so as you know, metallic lithium is high energy, lithium salts are low energy. So as the battery charges, the lithium is converted into what is its near metallic state and stored in the carbon. As the battery discharges, the lithium ions come back into the cathode, where it's stored primarily in an ionic form. And so that's what a battery is doing. It's shuttling lithium between two different oxidation states and electrons through the outside circuit. And what I'd like you to recognize here is that you have to not only be able to efficiently move the lithium, you have to be able to efficiently move the electrons. And so these structures are necessarily porous. And the porosity allows for the lithium transport, but they're also interconnected, and that allows for the electron transport. And really everything I'll show here is an optimization problem of how to control this porosity and control this transport to combine both power and energy in ways which are attractive. So if you're going to increase power and energy, there is a number of new materials that have been developed over the last 10 years, and this has led to incremental, a few percent per year improvements in energy. And so what traditionally was, say, lithium cobalt oxide, you learn to dope this with a little bit of iron, a little bit of aluminum, a little bit of manganese, and each of these steps, which is now 5 to 6 element systems, gives you a little bit more energy density. However, we've decided to go down the direction of reducing the transport lengths. It's a Fickian problem, it's a diffusion problem. And so if the diffusion lengths are very short, the rate production or rate capability is very high. And so then the question is, how can I keep all of my characteristic length scales short while maintaining a high volume of active material? And so a variety of approaches have been proposed, including interdigitated arrays. But again, think about scalability. I want a ton of this material, not a gram of this material. And so the approaches you use cannot be expensive top-down patterning technologies unless you come up with a really intelligent way to scale that. And so starting with these colloidal approaches, and the colloidal crystals we liked, again, because they can be self-assembled, and in fact, for a battery, unlike for the photonics, a few defects don't matter. So in photonics, we would worry about defects all the time. Here in batteries, you don't need to worry about that at all. You get a small decrease in energy, but not much. And so you can self-assemble this structure, and then electroplate material into that. So now these are relatively scalable approaches. But the trick is when you remove the particles, you end up with very, very small openings. And it's only because I was fortunate to take an ECE class as a graduate student. And in fact, I don't remember much of what I learned. I probably got a fine grade. But what I do very remember Professor Joe Leiding telling us was that if you want to get high vacuum in your chamber, you must electropolish the chamber. And so electropolishing, of course, is electrochemically removing material. And if you do this appropriately, you can uniformly open up the chamber and remove all of the burrs and all of the surface roughnesses. And so what we realized was that we could take our metal structure here, electropolish that structure, and open up, creating a structure which was about 90% open voids. So I also learned a little bit about scanning probe in the course, and perhaps that's turned out not to be as useful for my individual research career, but you know, it's one of those things. It's not what you expect to learn, it's the thing you didn't expect to learn that really mattered. And so by electropolishing, it creates this very open metal foam, and then we coat that with active material. And so this is the stuff that stores the energy. And so now we come up with ways to deposit a lot of the storage material and leave a little bit of a pore. And that, in essence, provides a fast pathway for lithium, a fast pathway for electrons, and a lot of active stuff in between. And so there, what you can see is the diffusion lengths are short, but the total volume fraction of material is high. And so the rest of what I'll show you is just the details. And so this is the metal foam, for example, here. This is a metal foam which is 90% air. These foams down here are 95% air, 5% metal. So the metal's an effective current collector. In the battery design, now this is the active material. These are just SEM micrographs, and we both made a nickel metal hydride and lithium ion systems. And it's just a difference whether you're storing the energy in nickel oxyhydroxide or, in our case, lithiated manganese oxide. And it's, again, you can see the coded framework, but this is the stuff that actually stores the energy. Everything else is just providing transport and providing the electrical and the ion transport. So what becomes interesting is if you take, and this was our first battery, this is a nickel metal hydride system, so the one still used in hybrid vehicles, not really in portable electronics anymore. But normally if you would take this battery and you would discharge it, a 1C discharge means 1 hour. And so if you take an hour to discharge a battery, you'll get most of the energy out and you can charge it up. And I'm sure you're familiar with that. Your laptops or cell phones, they typically take about an hour to charge. And you don't really run them in a regime where you would discharge them faster than an hour anyway. If you buy an electric vehicle, even if you fast charge a vehicle, you're talking probably 30 minutes to an hour. And that is due to a variety of reasons. One is the battery. If you quickly charge the battery, it can damage it. The other, of course, to keep in mind for any of you that say, oh, this is great, we'll just put these in cars, If you want to fast charge an electric vehicle, you need about 1 megawatt per car. And so to feed 1 megawatt into a vehicle, you can imagine there's some power handling issues, ignoring getting 1 megawatt to the fueling station in the first place. So fast charging vehicles would be wonderful, but go ahead and do your Ohm's law calculation and figure out what size wire you need to feed your vehicle. And you'll see that we're probably not going to have cars that charge in a minute anytime in the near future. 10 minutes is actually not such an unreasonable number. Now you're talking a few hundred kilowatts, and at anywhere between 500 and 1,000 volts, you can handle that. But in this system here, we now discharge at 1,000 C. So that's discharging the battery in 3 seconds. And so we discharge it in 3 seconds, and we still get 75% of the energy out. In a conventional battery, once you hit about a 2-minute discharge, most of the energy is simply dissipated as heat. And all we've done here is, this is just Ohm's law. All the internal resistances are extraordinarily small, and so you can pull the power in and out of the battery quite rapidly. So we did this also in lithium-ion systems, which of course is what is perhaps more technically relevant today, and we see similar results. The discharge curve isn't as flat. I'd be happy to discuss those details over lunch if people are interested. But again, now if you do a 10-second discharge, you get about 75% of the energy out. So very high charge and discharge characteristics. And again, that's because of the efficient pathways for moving what's important, electrons and ions. This is, again, a half cell. We'll ignore that. This is a real battery now. This is using our cathode with a conventional graphite anode. It turns out the anodes are a little bit faster. And what I'd like you to see here, these are charge curves. So in 60 seconds, the battery is 80% charged. In 2 minutes and 120 seconds, it's about 90% charged. And after about 10 minutes, it's fully charged. And so the discharge follows the same characteristics. You can get about 80% of the power out of the battery in about 1 minute. And so that's really a design space that has not previously been available. Oops. So something fun. So far we've talked about conventional materials, and we'd really like to go to some of these materials that have much higher energy density. So you may have heard of silicon. Silicon's an outstanding material for storing lithium with 1 or 2 minor problems. The first minor problem is that when you insert lithium into silicon, its volume changes by up to 300%. So how do I design a battery inside a steel can where one of the electrodes is changing in volume by nearly a factor of 4? And so what a number of groups, and this is a paper that Peter Noten and his group at Eindhoven published a year or so ago, is they make the silicon in a honeycomb structure, and so it simply buckles and comes back. And so it reversibly undergoes reversible buckling and contraction, and so that handles the strain. Why silicon is it stores 10 times more energy than carbon per unit volume. There's another issue that it reacts with electrolyte and forms a polymer film on the surface, and it turns out that polymer film gets cracked when it expands and contracts. And so this only solves half the problem. The other half the problem is one that has yet to be solved by anybody, but there's some interesting efforts going on. And so we went ahead and did a similar structure using silicon. The pictures look the same, the physics is the same. And what we find here is this is actually, the silicon is only present as a thin film. It completely fills the pores when it lithiates and then shrinks back up against the walls when it delithiates. So this is a way that we can overcome the swelling problem. The silicon's trapped. This does not solve this polymer film, this SEI layer, and so it starts to form. And so these don't actually work in what you would call commercial applications. They work for about 50 cycles, and then they eventually fill up with this polymer crud, and they die. So in some sense, we're going to depend on the community to start solving this problem, and maybe we'll solve it, or if not, hopefully someone else will. But why we're interested is, at least for 30 cycles, we have capacities here which are on order 3,000 milliamp hour per gram. If you compare that with carbon, which is about 300 milliamp hour per gram. So there really is the potential here, I think, to, again, increase the energy. And it is also by using these sort of properly designed three-dimensional scaffolds to provide the characteristic properties you need. So I'll just take 1 or 2 minutes here. Thermal physics in batteries matters too. If you imagine when you charge and discharge a battery, there's a lot of heat being evolved. And so we're trying to understand how the thermal properties of the constituent materials change. And it turns out that they change rather dramatically. So David has developed this wonderful technique for measuring thermal properties of thin films. I'd encourage you to just look at any number of his references for this. But basically, we build a small lithium-ion battery in a sort of a non-traditional configuration, so we can bring in a laser, which we use then to measure the heat capacity and thermal conductivity of the material. And so we can still cycle the battery in a traditional fashion, and it follows what you'd expect in the current versus potential. But what's intriguing is that the thermal conductivity of this cathode varies by a factor of 2 between the charge and discharge state. And so as you start to charge and discharge batteries more rapidly, and you start to think about how do I get heat in and out of the battery, well, it turns out that the thermal properties of the constituent materials are not constant. They're evolving, and they're evolving actually in a nonlinear fashion. As you charge the battery, the thermal conductivity first increases rapidly, and then it remains about constant. And then as you discharge it, it's about constant, and then it'll start to fall off at the end point. So I think this will be something that as heat evolution becomes more important, we're not going to be able to simply use either a linear extrapolation or just assume a constant value. So hopefully I've shown you some of the opportunities here for nanostructuring of electrodes. Again, in very traditional materials. The materials we've used, these lithiated manganese oxide, is something that's been around for probably 20 years now. But really what the nanostructuring does is it offers opportunities for an ion and electron management as long as you understand the critical dimensions of the material's chemistry. What I've shown here are mostly large format batteries. What James was talking about yesterday were primarily micro batteries. The physics is the same. It's really what application space and what design space you may be more interested in. So with that, I'd like to just acknowledge again a few people. Kevin Arpin, James Pekel, and Junji Wang were graduate students who work on this. Jiyoung Cho and Huaigang Zhang, postdocs. And then for this specific project, we've collaborated a lot on the thermal physics with David Cahill and some of the micro battery work with Bill King. So. Thank you very much.
Very efficient. We've got time for a couple of questions.
And I'll head out too.
Somebody's got to have a question. Or that was the only thing you learned in an electrical engineering class?
It's the only one I ever took.
You should have taken one for me.
I was too scared.
See, that's why he's a professor. Smart. Well, let's thank our speaker and all the speakers today.